Section 8.3, testing difference between means with dependent samples. We talk about dependent samples. I mentioned this a little bit in the previous couple sections. We're talking about before and after of the same sample, such as, for example, you want to see what this statistical variation is of someone who took before someone took a medicine and that same person after someone took a medicine. These are paired. You want to look at before and after the same individual. Let's suppose we're looking at medicine to lower cholesterol. We look at the individual A, cholesterol level before, and then same individual A 6 months later after taking the cholesterol drug. So while it doesn't have to be random, we do have to pair them. And that's what I mean. We have a before and after. And we assume the populations are normally distributed, or the n pair of points is at least 30. What I mean by that is it's not 30 points, like 15 people before and after. It's actually 30 individual people before and after. Now, the formula here, again, this is not hard, but it is rather convoluted. You need to find several things. We're going to use the t-table for this. But before we do that, we have to find our distribution levels. And we find that this right here is the sum of the d's distribution. Over here is the sum of the d squared minus sum of d squared over n, all over n minus 1. And then you put the formula in here, the average difference minus the mean over my s sub d, which is my sample deviation, over square root of n. We still do a null and alternate hypothesis, and it'd be better to just go through some examples here. So let's look at an example here. Shoe manufacturer claims that athletes can increase their vertical jump heights by using the manufacturer's training shoes. And I assume this would be probably used by basketball players and their coaches, maybe long jump and high jump and track. But that's probably the primary targets for this. Vertical jump heights of 8 ranks, like the athletes are measured. After the athletes have used the shoes for 8 months, their vertical jump heights are measured again. Vertical jump heights in inches for each athlete is shown in the table below. The alpha 0.10. Enough evidence to support the manufacturer's claim. Assume the vertical jump heights are normally distributed. So I've got 8 athletes here, and they recorded their heights they jumped before they got shoes and 8 months later after they got shoes, such as athlete 1 here jumped 24 inches. The first time, 8 months later, 26 inches. Second one, 22 inches. And then after 8 months, 25 inches. The third one before the shoes, 25 inches. 25 inches after the shoes. So I'm going to do my null alternate hypothesis, and I'm going negative here because on the table, I'm subtracting the after from before. So what I'm doing here is actually, I'm doing the reverse of this. 24 minus 26. You could go the positive way, but when I subtract, I'm trying to be consistent here. So 24 minus 26 is minus 2. 22 minus 25 is minus 3. So my null hypothesis is the claim is it less than 0? That's why I'm doing that, because I'm subtracting the new from the old. And that means the null hypothesis will be greater than 0. Now, there's a couple things here. I've redistributed this table from here into here to use Excel. And I got before and after, the same information, 24. I got to find my d and then my d squared. 24 minus 26 is negative 2. 22 minus 25 is negative 3. 25 minus 25 is 0. And that adds up to negative 14. And then that negative 2 in the d I squared. Negative 2 is 4. Negative 3 is 9. 0 squared is 0. Negative 1 squared is 1. And so on and so forth. Then I add those up. So this is the sum of d, and this is the sum of d squared. Now, our mean d would be the negative 14 divided by 8, which is negative 1.75. We'll be using that in a little bit. Got to find my standard deviation now. As I said before, these are plugs and chugs. Plug it in, chug it out. They're not hard, but there are multiple steps. It's easy if you find everything properly first. So sum of d squared, which is this right here, 56, sum of d squared. Right here is 56, minus the sum of d, which is negative 14, squared divided by number of samples, which is 8. 50, that's 14, negative 14 squared is 196. So it's 56 minus 196 divided by 8, which is 31.5. And the denominator, that's number of samples minus 1, so it's 8 minus 1 is 7. 31.5 divided by 7 is 4.5. Square root it as 2.1213. So now we can finally find our t-score. It's my number, my d bar right here, the thing I found earlier, negative 1.75. As before, my u is assumed to be 0. So negative 1.75 all the way across here. And in the denominator, it's my sample deviation, which is 2.1213, divided by the squared number of samples, which is 8, which is 2.828. 2.1213 divided by 2.818 is 0.750. Negative 1.75 is divided by 0.750 is negative 2.33, which I've got right here. But let's see what our make or break is here. Alpha is 0.10. It's one-tailed. So if I go alpha 0.10, one-tailed, here's my one-tailed. It is 0.10. There it is right there. And I'm going to go down. We had 8 samples, so it's 7 degrees of freedom right here. So 7 degrees of freedom with one-tailed at 0.1 would give me 1.1415. Is left-tailed, so it's negative 1.1415. And 1.1415 is right here. Anything to the right of this, I'd fail to reject. Anything to the left of this, I would reject. Actually, add to the left of this. And negative 2.33 is less than negative 0.1415. So I would reject the null hypothesis. And there's enough evidence to support the manufacturer's claim. Here's another example. Shoe manufacturer company claims that the athletes can decrease their time in a 40-yard dash using the manufacturer's shoes. 40-yard dash times a 12-hour second. Athletes are measured after the athletes have used their shoes for 8 months. 40-yard dash times are measured again. Their time in seconds is listed below at alpha 0.05. Number and support the manufacturer's claim. I'll assume normally distributed. So I've got 12 individuals here, and I've done the same thing as did before. 4.85, 4.78. And what I've done is I've made it right-tailed this time. So, and that's because I'm subtracting from before. I want to do it in the right time. You can do either side. I'm going, this time subtracting 4.78 minus 4.85 rather than 4.85 from 4.78. And at first one I get 0.07, 0.07 squared is 0.0049. So my sum of D is 0.28. My sum of D squared, where I squared everything, I'm terrible artist here, and I apologize for that. Sum of D squared is 0.047. And as I said before, it's a plug and chug. 0.28, which is what my sum of D is, divided by number 12 samples, 0.0233. We'll use that in a little bit. Let's find our standard deviation. Sum of D squared, which is 0.047, minus the sum of D squared, 0.28 squared, over 12, which ends up being 0.00653. 0.07 minus 0.00653 is 0.0407. In the denominator, I got 12 samples, but it's 12 minus 1, so it's 11. 0.0407 divided by 11 is 0.003679. Square root of that is 0.0607. And that is my sample deviation. And that's going to go right here. 0.0607. So now I've got my 0.0233, which I had from the beginning here, divided by 0.0607, divided by square root number of samples, which is 12. So 0.0233 divided by 0.0607, divided by square root of 12, which is 0.3464. 0.0607 divided by 0.3464 is 0.01752. A lot of tiny numbers here. So my T critical is 0.0233 divided by 0.01752, which is 1.33. Here is my 1.33 right here. Let's find our T critical. We've got 12 samples, so it's 11 degrees of freedom. It is one tail, it's right tail, so it's going to be positive here. And that is going to be, let's see, 11 degrees of freedom, and we're looking at alpha 0.05. It's one-tailed, alpha 0.05, so it would be 1.796, which I got here. It's positive 1.796 since it's right-tailed. And again, as before, the arrow is pointing towards the right on the alternate hypothesis. And this is the make or break right here. It is to the left where I failed to reject. And this is the reject side on the right. So it's within that. So we reject the null hypothesis, which is that it is less than 0. So we cannot support the manufacturer's claim that reduced the 40-yard dash. A couple more here. These are going to be two-tailed ones. Campaign staff for a state legislature wants to determine whether the legislature performing rating from 0 to 100 has changed from last year to this year. The table shows below legislature's performance ratings from 16 randomly, the same 16 randomly selected voters from last year and this year. And I guess, like I said, getting rating from 0 to 100. So the prior year, for the person number 1 gave a 60, and then the current year they gave 56. And 60 minus 56 is 4. Number 2 is 54 minus 48, which is 6. And I've done the same thing as before. I just converted this table in Excel, so it's easier. My sum of D for all these differences is 53. My sum of D squared is 1581. And I'm going to plug and chug. My sum of D first is 53 divided by 16, which is 3.3125. When we use, that's my D bar. We use that in a little bit. They want to know if it's changed or not. So is it equal? That means it's the null hypothesis is equal something. If it has changed, doesn't matter plus or minus, that is where the claim is. They are looking for the claim if it's changed or not. So I got my 1581 here, which is my D squared minus my sum of D, 53 squared, divided by number of samples, 16. It's 1581 minus 175.5625, which is 1405.4375. In the denominator, 16 samples minus 1 is 15. And that 1405.4375 divided by 15 is 93.7. Square root of that is 9.68. So I have my S of D right here. And we already got our D bar, which is 3.3125 right there. 3.3125 divided by 9.68 divided by square number of samples, which is 16. Square root of 16 is 4. So it's 3.3125 divided by 9.68 divided by 4, which is 2.42. 3.3125 divided by 2.42 is 1.37. And that is what I got here, 1.37. And it wants to know alpha 0.01 is two-tailed. So let's look at, by the way, there is 16 samples. So there's 15, there's 16. So there's 15 degrees of freedom at two-tailed. at 0.01 right here. And let's see where these meet. And that would be 2.947. So it's going to be negative and positive 2.947 on my critical points. Anything left of there, I reject. Anything to the right of there, I reject. And guess what? It falls in the failed to reject between those two, as 1.37 is less than 2.974 and is greater than negative 2.974. So we support the claim. I mean, we support the null hypothesis. It means we can't support the claim that's changed. Medical researcher wants to determine whether a drug changes a body's temperature. In other words, when you take the medicine, does it change your temperature? 7 test subjects are selected, and the body temperature in Fahrenheit is measured. Subject given a drug, and 20 minutes later, the temperature is measured again. The results are listed below, and they had 7 individuals here. Took their temperatures before and then 20 minutes later. So, as before, I put a table here, 7 individuals. It is, well, I know it's changed. So that is a null alternate hypothesis equal to or not equal to. If the sum hasn't changed, it'd be equal to 0 on average. But if it has changed, then it won't be equal to. It doesn't matter if it's higher or lower temperature. So I found the differences. These temperatures, summed them all up, I get 3.9. 3.9 divided number of samples is 0.557. And we'll be using that in a little bit, my d bar. Then I got my 7.29 for my d squared, and plug it in. 7.29 minus my sum of d squared, which is 3.9, divided by 7. That ends up being 7.29 minus 2.173, which is 0.5117. In the denominator, I got 7 samples minus 1 is 6. 0.5117 over 6 is 0.853 squared root. That's 0.923. That is my sample deviation. My D, as I found before, D bar is 0.557. And then my sample deviation, 0.923, divided by the square root number of samples, which is 7. That's 0.968 over 2.65, which is 0.3652. 0.557 over 0.3652 is 1.53. 1.53 is right here. We are looking at alpha 0.05, and there's 7 samples. It's two-tailed because it's equal and not equal. If it's 7 samples, that's 6 degrees of freedom right here. 6 degrees of freedom at alpha 0.05 for 2 tails would be right here, 2 tails. That's 2.447. So it's plus and minus 2.447, which is here. And 1.53 is greater than negative 2.447 and less than positive 2.447. So we cannot support the claim, but the null hypothesis we would fail to reject.